In this video, we work our second example problem in which we're solving an IVP with the Laplace transformation, and the differential equation has variable coefficients. So notice that if you look at this, this is not a constant coefficient equation. It is not a Cauchy-Euler differential equation. So all of the methods that we've studied previously won't work. But since we have a variable coefficient equation where those variable coefficients are just polynomials in t, and we have some initial conditions, the Laplace transformation method is an appropriate method to solve this, and we should be able to find a function y of t that satisfies this differential equation and satisfies those initial conditions. Again, we are assuming that y, that is the solution of the differential equation, is a piecewise function of exponential order, and then we'll use the method to solve this. So we always start this method in the same way. We introduce our notation so that the reader knows what that capital Y represents. We're going to let the Laplace transform of little y equal big Y, and we'll take the Laplace transform of the differential equation. We always start there. Since the Laplace transform is Laplace transformation, is a linear operator, the Laplace transform of the left-hand side is just a sum of the Laplace transforms of each of the terms. So we'll have the Laplace transform of y double prime plus the Laplace transform of t times y prime minus 2 times the Laplace transform of y equals the Laplace transform of 4. Now, we had a theorem for this, and that theorem said that if you have the nth derivative of some function and you're taking its Laplace transform, the Laplace transform would have n plus 1 terms, and they have this structure. If n is equal to 2, we start with s squared. So we always start with s to the n. And then we subtract other terms, and for each term, we're going to see a factor of s, and those powers of s will decrease. So we'll have an s squared term and an s to the first term, and then lastly, we would have an s to the 0 term. So I'll have 3 terms for the Laplace transform of the second derivative of y. And then each of these powers of s will be multiplied by a function. The first function is the Laplace transform of little y, which is big Y or capital Y of s. And then as we go from left to right, you're going to increase the order of the derivative like this. This is little y at 0 and little y prime at 0. So that's the Laplace transform of y double prime. The Laplace transform of t times y prime is a little bit more challenging. So I think what I will do is I'm going to leave some space for that right here, and I will get back to that in just a moment. And then we have minus 2 times the Laplace transform of y, which is big Y of s by definition up there. And then the Laplace transform of a constant is that constant over s. Okay, so the only one that we really need to take care of is this, and that requires us to use that formula that we derived earlier for the derivatives of a Laplace transformation. So we said that, or we were able to show earlier, that under certain conditions, the Laplace transform of t to the nth power times f of t is negative 1 to the n times the nth derivative with respect to s of f of s. That's the Laplace transform of little f of t. Now, in practice, we don't typically use this. If I have t squared times sine of t, I probably wouldn't use this formula. Usually we have expressions that look like t to the n times a sine of kt in our table of Laplace transforms. But if I have a term that looks like this, so that I'm solving a differential equation with variable coefficients, and those variable coefficients are polynomials in t, this is very appropriate here. So I'm going to apply this to this. Here we have a t to the first power, so n is equal to 1. This is sort of an aside. We're going to come back up here and fill in just this term. So if n equals 1, so according to this rule, we'll have -1 to the first times the first derivative with respect to s of the Laplace transform of this function. That's the Laplace transform of y prime. So we'll have -1 times the first derivative with respect to s of the Laplace transform of y prime, which we also have a theorem for. The Laplace transform of the nth derivative has n plus 1 terms. Since this is a first derivative, we're going to have 2 terms. We start with an s to the first, and then we decrease the powers of s, then we'll have an s to the 0 here. The first term is always positive, the other terms are always negative, ignoring the signs of each of the factors. And then we'll take this factor s and we'll multiply it by y of s. That's the Laplace transform of little y of t, and then we'll subtract little y at 0. And then this value is given to us in our initial conditions, just happens to be 0 this time. And now I have negative derivative with respect to s of a product. That's y of s, which is unknown, times s. So I'll have to use the product rule here. If I call that my first function and that my second function, this will be -1 times the derivative of the first times the second plus the derivative of the second times the first. And I'll just put that factor out front. And if we want, we can distribute the negative now. So you have -y of s minus s times y prime of s. That is the Laplace transform of t times y prime. So that's what goes right here. So we'll have a -y of s minus s times y prime of s. So this is the Laplace transform of y double prime plus t, or the Laplace transform of t times y prime, which is this, minus 2 times the Laplace transform of y, which is y of s, equals 4 over s. So that's the Laplace transform of the differential equation. And y of 0 is 0 from the initial condition, and y prime of 0 also happens to be 0. Now notice that this time we don't just have an algebraic equation involving y of s, we've got a first order differential equation. So we need to rearrange this first order differential equation and see what methods from our unit on first order differential equations would be appropriate for solving this equation. So I'm going to try to write it as first order linear, and we'll see if that actually works. So I've got -s times y prime of s. That's one of my terms. And then let's see what else. I need y of s terms. I've got minus s squared, or sorry, positive s squared times y of s minus y of s minus 2y of s. So that's going to be s squared minus 3 times y of s. And this is 0 and this is 0. And so we just have 4 over s on the right-hand side. So that actually is first order linear in y of s. It has a coefficient, so we'd have to divide that out. But after we divide that out, I'll have the derivative plus a function of s times the function that we're looking for equals a function of s. So we can solve this differential equation with an integrating factor. And of course, dividing by negative s is the same as multiplying by 1 over negative s. And so we get this. I have y prime of s here. And then if I divide each of these terms by s, I think I'll make the positive term, or I'll write the positive term first. -3 over negative s is positive 3 over s. And then we're subtracting s squared divided by s, which is just an s. And then we'll have a -4 over s squared on the right-hand side. Remember how we saw the first order linear equation? Actually, I think I'm going to write my steps on the right-hand side as well. So typically what we would do, there we go, is we would identify P of S, that's the function multiplying y here, and then compute its antiderivative. And then the integrating factor is e to that power. And then we take the equation and we multiply by the integrating factor after we simplify that. So in our case, P of S is this 3 over S minus S. And so if I want to anti-differentiate that, the antiderivative of 3 over S is 3 times the natural log of the absolute value of S. And here, if I'm taking the antiderivative of negative S to the first, I add 1 to the exponent and I divide by the new exponent, and typically I add C. And then we are going to take E and raise it to this power, and that will be our integrating factor. Now, typically we choose C to equal 0 for reasons that we discussed when we discussed first order linear differential equations. Basically, the idea is we end up with this extra factor e to the C after simplification, and multiplying the entire equation by e to the C doesn't do anything. We don't need infinitely many integrating factors, we just need one. So if we let C equal 0, we just get one of them. So we'll have e raised to this power. And then we can use a little bit of algebraic manipulation to simplify this. Remember from pre-calculus that if we are multiplying two power functions like this, we just add the exponents. That's going to be true no matter what the base is. If the base is a variable or the base is a number, this property still holds. And it also works in reversed. So if you have a sum of two expressions here in an exponent, you can always rewrite this expression on the right as a product like this. So we'll do that right here. And also, I'd like to simplify the e and the log, but I can't because of that 3. So I'll use this property from algebra. If you have a constant in front of natural log of a, you can bring that constant inside and make it a power for a. So this is the same as e to the natural log of the absolute value of s cubed times, because of this property, e to the negative 1/2 s squared. And then since e and the natural log are inverse functions, these guys undo each other, and we would just end up with the absolute value of s cubed. Why don't we just make that s cubed? And we'll assume that s is greater than 0. If s is less than 0, this would just be a -1 times s cubed, but then we're going to multiply the differential equation by that anyway. So multiplying everything by an extra -1 factor, a factor of -1 is not going to change things. So we have this. Okay, so that's our integrating factor. And now we want to multiply both sides of the differential equation by the integrating factor. When we do that, the left-hand side should be the derivative of y times the integrating factor. So I have this differential equation, which I'm going to call dE star. This one up here, the differential equation y prime of s. And I'm taking that and I'm multiplying by the integrating factor, which is this. So we'll have y prime of s plus the integrating factor times this expression equals -4 over s squared times the integrating factor. And our integrating factor is s cubed times e to the -1/2 s squared, or you can call that -s squared over 2 if you want. And then 2 of these s's will reduce with 2 of these, so we'll just have a -4s there. And then if we simplify this, let's see what we get. Got s cubed times this exponential times y prime. And if I distribute the s cubed times the exponential times 3 over s, one of the s's will reduce. So we'll end up with 3s squared times negative s squared over 2. And then if I take this and I multiply by negative s, I'll have a negative s to the 4th times the exponential. All that's multiplied by y, and that equals negative 4s e to the negative s squared over 2. So we've simplified, and our hope is that this left-hand side is the derivative of y times the integrating factor. This is the derivative with respect to s. And I guess that is a bit of a question because this was our integrating factor, right? So we want to recognize that the left-hand side is this derivative of y times the integrating factor. Now, with something that looks like this, I would certainly check, just in case we made an algebra mistake, just in case we're tired and we make an integration error, something like that. It's always a good idea to check your work as you go. So just as an aside, let's check. We would have derivative of the first times the second, which is right here, plus derivative of the second, which would have to be this, times the first. So when we check, we're really just checking that the derivative of this expression is actually equal to this one. Well, if this is my first factor and this is my second factor, as we're both functions of s, I would use the product rule to compute the derivative. We would get the derivative of the first, which is 3s squared times the second, plus the derivative of the second. Derivative of an exponential is e to that power, times the derivative of the inside by the chain rule. Derivative of the numerator is going to be negative 2s, and then we divide by 2. Or you can think of that as a constant of 1/2 that you're factoring out and then multiplying through. So this is the derivative of the second, and don't forget to multiply it by the first function, which was s cubed. The 2's reduce, and we have 3s squared times our exponential. And then we'll have a minus s times s cubed is minus s to the 4th times e to the negative s squared over 2. Is that what we have right there? It sure is. Okay, that's great. So we know we did everything that we were supposed to do, and that means we were 2 steps away from getting y of s by itself. Okay, so I've got the derivative of this product is equal to that. In order to get rid of the derivative, we will take the antiderivative of both sides with respect to s. And this little check was a different line of thought, so I'm going to try to isolate that from everything else. The antiderivative of the derivative is the original function. It's just y of s times the integrating factor. Now I see a product. So I'm thinking, okay, I either have to use u substitution or integration by parts, and then I ask myself which one of those is appropriate here. And I'm using WRT for with respect to. Well, if I'm trying to decide between integration by parts and u substitution, I always try u substitution first. I've got e to some power. I'm thinking, if I take the derivative of this, the inside function is negative s squared over 2. If I take the derivative of this, do I have a constant times s as its derivative? If I do, well, then that will work. I'll be able to write everything here in terms of u. And it actually turns out to work. the derivative of a constant times s squared ends up being a constant times s. So we'll use u sub here. And you can write it like that if you want to, or you can write that u as -1/2 s squared. Then du is -1/2 times the derivative of s squared, which is 2 times s to the first, times ds. The 2's reduce, and now I've got a -s ds is equal to du. It's close to what I have up here, but not quite. I need a -4s ds. So I'll multiply both sides of this by 4. So 4 du is -4s ds. So that's my 4 du. And that's an e to the u. So we write the entire integral, or the integral, excuse me, entirely in terms of u. And then that's very easy to anti-differentiate. The antiderivative of 4 times e to the u is 4 times e to the u plus c. And then don't forget to back substitute. U is actually -s squared over 2. Okay, so we've anti-differentiated both sides with respect to s. We used a u substitution here. We identified u, we computed du. We wrote the integral in terms of u. Then we anti-differentiated, and then we back substituted. Okay, now big picture, we're still trying to find y of s, or at least like that's the big picture at one level up from the level that we're on right now. If I want to get y of s by itself and y of s times this is equal to this, well, then I just need to divide both sides by this. So I guess I should have written this down a number of times. Just so that we have a bunch of equivalent statements there, equivalent equations. And we're trying to get y of s by itself, so we will divide both sides by s cubed times this exponential. And so now we have y of s is equal to this expression. And since this is a monomial, or you can think of it like a monomial, it has a single term. There's nothing that we're adding or subtracting here in the denominator. We can take each of the terms in the numerator and divide them both by this s cubed times e to the -s squared over 2. Well, this divided by this will reduce, the exponentials will reduce, and we'll have a 4 over s cubed there. And then over here, we'll have c over s cubed times e to a negative power. But that is the same as this. If I bring that up to the numerator, this is c times an exponential raised to a positive power over s cubed. But that is our y of s. But notice as s goes to infinity, this term goes to 0, but this one doesn't. And this expression here, I've got an exponential over a third degree polynomial in s. As s goes to infinity, this is an infinity over infinity indeterminate form. But if I use L'Hopital's rule a couple of times to try to get rid of the infinity over infinity indeterminate form, eventually I would take the derivative enough times that I would end up with a constant in the denominator, and I would still have an exponential in the numerator. So I could show using L'Hopital's rule that this exponential over a polynomial function in s actually goes to infinity as s goes to infinity, provided that c is positive. If c is negative, this whole thing would go to negative infinity. So if c is positive, it goes to positive infinity, the term does. If c is negative, it goes to negative infinity. And both of those are issues. Those are not allowed if y of t is a function of exponential order and y of t is a piecewise function. Remember that initial assumption that we started with was right here. We're assuming that y is a piecewise function of exponential order. Well, in that case, the limit of y of s as s goes to infinity is supposed to be 0. That will always be the case if little y of t is a piecewise function of exponential order. So that means the only way that this term, well, I was going to say the only way the term can exist in the equation, but it's actually not going to exist at all. The only way that that condition is satisfied is if c is equal to 0. Because if c were positive, this goes to positive infinity. If c is a negative constant, this goes to negative infinity. The only way that this doesn't go to infinity or negative infinity is if c equals 0. So we will say that since little y of t is a piecewise function of exponential order, we're assuming that is a piecewise function of exponential order. We have that the limit as s goes to infinity of y of s is supposed to be 0. The only way that happens is if c equals 0. So that's this requirement implies that c must be 0. So in that case, y of s is just 4 over s cubed. And that looks a bit like this rule from our table. For the inverse transform of n factorial over s to the n plus 1, I get t to the n. I can use that to compute the inverse transform of this, which would give me y of t. Well, in our case, n plus 1 is 3, so n is equal to 2. So that means I need a 2 factorial in the numerator. So 2 factorial is the same as 2. So I would write this as 2 times 2 factorial over s to the third. And then we can take the inverse transform. So y of t is the inverse transform of y of s. And of course, I mean inverse Laplace transform. Oops. And the inverse transform of 2 times this function of s is 2 times the inverse transform of this piece, which is t to the n with n equals 2. So it's just 2t squared. Okay, so let's see, what did we do? We back substituted after we took our antiderivative here. Then we divided by the integrating factor to isolate y. Then we saw this term, we're like, that's really strange. I don't see anything like that in my table of Laplace transforms. And then we thought about the fact that the limit of this function as s goes to infinity must be 0 if little y of t is a piecewise function of exponential order. So that was enough to tell us that c would have to be 0 so that this condition would be satisfied. So let's say we'll use the properties of y of s to find the value of c. Then we've got y of s in a form that we can compute the inverse transform of just looking at our table. So then we compute the inverse transform. Okay, it looks like I ran out of space there. Might be better if I did this. There we go. Okay, so let's review the method. It's actually not too bad at all. We had a differential equation. That differential equation had a variable coefficient, and the variable coefficients in this case were polynomials in t. If the variable coefficients are polynomials in t, we're going to be able to use the derivatives of a transform, Laplace transform, in order to compute the Laplace transform of the left-hand side of the differential equation. So if we have variable coefficients, we know we're going to use this fact, but otherwise we just do this the same way, pretty much the same way as we would solve any other initial value problem. We introduce our notation, we take the Laplace transform of the differential equation, we use the initial conditions to simplify the equation. Whenever you've got a t or power of t times y or one of y's derivatives, you're going to use this fact, and then you substitute, and then you look at the equation, and because of this fact, because we have a derivative with respect to s here, an nth derivative with respect to s, when you take the Laplace transform of this, rather than turning it into an algebraic equation in y of s that you just solve for y of s, it's going to be a differential equation. For the most part in our class, it'll be a first order differential equation, often solved with an integrating factor and occasionally sometimes solved with the separable differential equation method. It tends to be separable when that right-hand side is 0 and the initial conditions are such that you don't end up with a non-homogeneous term on the right-hand side. So we had a non-homogeneous term in ours. So this was a first order linear equation in y of s. So we solved this by using the integrating factor method. We identified p, we computed its antiderivative, we defined the integrating factor to be e to that power. We chose that constant to be 0 because we don't need infinitely many integrating factors. We just need one. So we just chose the one that would give us, that would correspond to having this constant equal to 0. And then we multiply the differential equation by the integrating factor and simplify. And then when we do that, we said, hey, this is a first order linear equation. The only way that happens is since this is a first order linear equation, after multiplying by the integrating factor, I would expect the left-hand side to be the derivative with respect to s of my function that I'm looking for, in this case y of s, times the integrating factor. And so we said, let's recognize the left-hand side as that derivative of that product and then check by computing the derivative of the integrating factor and seeing that it's actually equal to this function that's multiplying y of s. So it checked out. That meant we were 2 steps away from getting y of s by itself. To get rid of this derivative, we anti-differentiate. And then once we anti-differentiate to get y by itself, we just divide by the integrating factor that's multiplying it. And then we end up here. And then this is one other thing that is a little different about solving an IVP where the differential equation has variable coefficients. Sometimes you're going to end up with terms in y of s that don't satisfy this condition. As s goes to infinity, y of s is supposed to go to 0 if little y of t is a piecewise continuous function. I forgot the word continuous there. A piecewise continuous function of exponential order. So we said, okay, if we are assuming that y of t is a piecewise continuous function of exponential order, then this limit is supposed to be 0, which means that value, or this term, has to be 0, which means that c has to be 0. So we use that fact to get c equals 0, and then we do what we always do. We look at y of s, we try to do some pattern matching, by looking in those right columns in our table of Laplace transforms, trying to go from the transform to the original function of t. And we see that since this is a 3, n plus 1 is 3, n must be 2. And that means I need a 2 factorial in this numerator. So we break up that 4 into a 2 times 2 so that we can take the inverse transform. So this is just 2 times the inverse transform of that, which is t squared. And that's that. Now, if you want to check and make sure that this satisfies both the initial conditions and the differential equation, it's actually a pretty easy check. The first derivative of this is just 4t, And let's see, the initial conditions say that y of 0 equals 0 and y prime of 0 equals 0. At t equals 0, this is 0 and the derivative is 0. So those check out pretty easily. And then over here, the differential equation says y double prime plus t times y prime minus 2y is equal to 4. Well, I guess I need to compute y double prime to check that. If y prime is 4t, y double prime is 4. So y double prime is 4, then we're adding t times y prime, which is t times 4t in that case, and then we're subtracting 2 times y, which is 2t squared. And if we simplify that, that's the left-hand side of that differential equation, but we've evaluated it or we've substituted in y double prime equals 4, y prime equals 4t, and y equals 2t squared. And we get this, and those guys reduce, and that's 4. And that's exactly what the right-hand side is supposed to be. So if we substitute in our y to the left-hand side, we do get 4. So this function, y of t equals 2t squared, is the solution to the differential equation, or is a solution to the differential equation, and it is of exponential order, and it's at least piecewise continuous on 0 to infinity. It's obviously continuous on 0 to infinity.